This is a National 5 Maths video and looks at Pythagoras in 3D shapes. We are learning how to calculate the length of a side or a diagonal in a 3D shape with Pythagoras. We will be successful if we know what a space diagonal and a face diagonal are, and we can identify these if required in a 3D shape, and then use Pythagoras' theorem to find a solution to the problem involving a 3D shape. So we're going to look at a few different 3D shapes. The first is a cone. So this cone has a perpendicular height, h, which is shown in red in the diagram, and a diameter d, shown in blue, and a sloping length, l. You can see here that the height meets the diameter at right angles. So this red line meets the diameter at right angles, creating then a right angled triangle inside the shape. Let's look at an example. Okay, so we have here a cone and it has a diameter of 5.5 centimetres. So that is this yellow line here measuring 5.5. A height of 12, so that is the vertical height of 12, and we have to calculate the side of length L. So we can model this by constructing a right angled triangle. So let me just use a straight line to create a little model of this right angled triangle. So we have our height of 12, the unknown length L, and this length here along the top meeting the height in the middle. And we can assume that that is a right angled triangle where that diameter meets the perpendicular height. Okay, so let's just put those measurements in. So we've got 12 here, the perpendicular height. We want to work out the length L, and this length here then would be halfway between the centre here and the outside. So half of 5.5 then, giving us 2.75. So to calculate length L, which is the longest side in this right angled triangle, we want to square and add the two shorter sides together. This gives us 151.5625. The length then is the square root of that measurement, which gives us 12.311, and it goes on. So let's round that answer to 12.3 centimetres, one decimal place. Okay, let's have a look at another example involving a cone. So these cones have a slant height of 45 centimetres and a base radius of 15. This time we have to calculate the perpendicular height of the cone. The perpendicular height of the cone is from the centre of the base to the top. So again, we'll model that using a diagram. So we want to calculate the height. We know the slant height is 45, and we know the base radius, so from the centre to the edge, is 15. So slant height is 45, base radius is 15. And we know that we want to calculate the perpendicular height, which meets this base radius at right angles. So we've got a right angled triangle. So to calculate the perpendicular height this time, which is a shorter side, I'm going to take the longest side and square and subtract the shorter side squared. And this time I end up with 1800. gives a height when we square root 1800 of 42 point, sorry, oops, that's going to be 42.426, and decimal goes on. So let's round that to, again, one decimal place, 42.4 centimetres to one decimal place. So that's how we can use Pythagoras theorem to help work out either the sloping length or the perpendicular height in a cone. Let's move on and look at a cuboid. So this cuboid here we can describe as a cuboid ABCDEFGH. It has 12 faces, 6 faces, 12 edges and 8 vertices. The vertices are labelled with capital letters and the edges can be described using these letters. So for example, this pink edge here could be described as G to H. Now, the next bit of information is new. The red line, A to C, goes on the diagonal between the two vertices on the bottom face of this cuboid. Therefore, this is called a face diagonal, since it lies on the bottom face of the cuboid. The blue line going from A to F goes through the space inside the cuboid and is therefore called a space diagonal. This one can be hard to visualise, so it's important that you can try and see that it's going from this front vertex A through the cuboid to the back vertex F, and it's a space diagonal. Let's have a look at an example. So this cuboid is labelled very similarly to that last example, with the capital letters at the vertices. The diagram shows AB is 3 centimetres, A to E is 4, and B to C is 12. We have to find the length of B to H. Now B to H is a space diagonal. It is going through the space in the centre here of the cuboid. And we have been shown here a triangle, and it's in fact a right angled triangle here at D. So we'll mark in a right angle. So we are calculating this longest side here. We would therefore need to know this shorter side here, which we do. It is 4. And we would also need to know this diagonal length here, B to D. Now we don't know that for the time being. Now these problems in cuboids tend to be very similar. They involve Pythagoras, but they involve Pythagoras twice. So in order to get the length B to H, we need to know this diagonal length here. So in fact, we're going to create a right angled triangle here on the base of this cuboid. So this bottom face, the base, we can see another right angled triangle here. So I'm going to just draw that right angled triangle now so that I can model what's going on. So I have the length here, B to C. I then have this length here, C to D, and the unknown here, B to D. And what's created there is a right angled triangle. So let me just mark in those letters. So B to C, which is 12, and C to D, which is 3. And I need to know B to D to help me to work out the end answer, B to H. So B to D is what's called our face diagonal. So we are going to do Pythagoras here, work out this face diagonal, B to D. So I can see that B to D is in fact hypotenuse. So I'm going to square the two short sides and add these two short sides together to give me 153. Now b to d is then the square root of 153. Now because I'm going to use this again, it would be unnecessary to get a decimal answer here. So I'm going to keep this as 153 squared root, which is called an exact value, because I am keeping it as a square root. I'm then going to use this exact value in my next triangle. So if I just scroll back here, now I have the length b to d. I'm going to now use that to help me in this larger right angled triangle, which is going through the space of the cuboid. So let me just draw out that larger triangle, and then we'll put in the measurements. So again, that makes a right angled triangle in the space. And I'll write in these letters here. So we've got B, H, and then D. So I've just worked out that B to D is in fact the square root of 153. And I already know that this height is 4. So I'm now ready to work out the space diagonal B to H using Pythagoras. So B to H is another hypotenuse. So I'm going to take the two short sides. So I'm going to take the square root of 153 and square it and add it on to 4 squared. Now if I square a square root, I do in fact just end up with the number 153. And that gives me 169. So b to h is the square root of 169, which you may know is 13 centimeters. So there we are. Space diagonal is 13 centimeters. Okay, let's have a look at question 2. So again, we have to work out the length of a space diagonal, this time Q. So P to Q is going through this space here. And I've already got a right angled triangle here constructed for me. So to work out P to Q, I would need to know this length here, which I don't, and this length here, which I do, which is 12. So I need to therefore work out the length of the diagonal going on the bottom face there, first of all. So let's create another right angled triangle, and we will draw a little sketch of that just here at the side. So the base measures 3, the side measures 4, and this unknown I'm just going to name x at the moment. So this is our face diagonal, and we've called x. So I need to work out the length of x first. So x squared is 4 squared add 3 squared, which is 25. So x is therefore the square root of 25, which is 5 centimeters. So that is the length of our face diagonal, which is what we needed to help us here. So now we have that length as 5. So now we can go on and look at working out the space diagonal, PQ. So PQ is in fact the hypotenuse here in this right angle triangle. And I'm going to use my new side that I have worked out, this face diagonal, which is 5. And I'm going to square it and add it to the other side, which is 12. And the total that gives me a 169. Okay. And from there I can get my square root, which gives me the length PQ of 13 centimeters once again. There we are. Okay, one last example. So we've looked at cones and cuboids. This last example looks at a pyramid. This pyramid has a rectangular base, and we are looking to calculate the height of this pyramid, which is shown by this red line. Now, within this pyramid, I am going to construct a right angled triangle to help me find the height. So I'm going to get a straight line tool here just to make that nice and neat. So if I construct a right angled triangle here, hopefully you can see that by extending the centre to C, I can then make a right angled triangle. I'm just going to draw this outside now, and we will use this not to start with, but we will use it. So let me just draw in here. So we want to calculate this height here, which is on this side. Sorry, let me just go back to the pen. So we want to calculate the height. We do not unfortunately have this length here, which I'm going to call x just now for the time being. And we do not know, sorry, we do know the sloping length here is 6. So we'll just put that on that side there. So to get length x then, which is this length from the centre out to C, I therefore need to use Pythagoras again. So I'm going to insert another line just to try and create another right angled triangle here on the base of this pyramid. So hopefully you can see that that little line I've added makes another right angled triangle. So again, let me just draw that down here at the side. So this time, this right angled triangle has a unknown side here of x. That's what we're trying to find to help us with this height over here. We do know this side here measures 4 from B to C. Our right angled triangle is only half of that, which measures 2. And then the other measurement that is going from the side to the centre is half of 5. So this side here is therefore going to measure 2.5. This triangle here then is going to help us to find that missing side x, which is our face diagonal, since it lies on the face of the base. So we're going to first of all find the face diagonal x using Pythagoras. So we can see that 2 squared plus 2.5 squared is going to give me x squared. So this time that gives me 10.25. And therefore x is the square root of 10.25. And again, I'm going to leave that as an exact value. Over here then, I now know the value of x. So I'm now ready to find out that space diagonal, that vertical height h. So I can see this time that h is in fact a shorter side. So I'm going to now do Pythagoras, but I want to do a subtraction sum. So it's 6 squared minus the square root of 10.25 squared. And entering that into the calculator then gives me 36 minus just 10.25. Oops. Put that back over here. So the height then is equal to the square root of 25.75. Gives an answer of 5.074. So it's one decimal place. We'll call it 5.1 centimeters for the height. So, when we're using Pythagoras in 3D shapes, if we're dealing with a cone, we're dealing with the slant side. If we're dealing with a diagonal inside the shape, we have to consider Pythagoras twice. So we consider the face diagonal first of all, and then the space diagonal. It is important that you draw a sketch to help you with this. So let's just review the steps that we need. So if we're dealing with a cuboid, which is probably the more popular question, certainly in previous years, not the only thing that could come up, we want to think about, first of all, the diagonal we want to find the answer to and what we require from that. So we want to think about finding out, let me just get rid of that, about the face diagonal first of all, and then second of all, the space diagonal, which means that we're going to do Pythagoras twice.